Yeah, so welcome. Thank you very much for joining me on this panel discussion on operationalizing of AI standards. So my name is Lukas Spruch. I'm an associate professor of mathematics in the University of Edinburgh and a program director for finance and economics at the Turing Institute. And I have a great panelist today, Professor Marta Kwiatkowska from Oxford, Professor Sam Cohen, also from Oxford, and Professor Michael Robustness from Edinburgh. So maybe first, if you could, each of you tell us a little bit about your background and what's your area of expertise. I don't know, Marta, do you want to start?
Okay, good afternoon. I'm Marta Kwiatkowska. I'm a professor at the University of Oxford. I'm a computer scientist. For quite a few years now, I have been working on techniques to verify various systems correct, especially probabilistic systems. And in particular, these have been applied in many applications in robotics, in DNA computing, nanotechnology, security, etc., and etc. But for the past 3 or 4 years, I have focused on AI, machine learning, and I've started developing verification for these beasts, so to speak.
Thank you. Sam?
Sure. So I'm Sam Cohen. Good afternoon. I'm a mathematician also at the University of Oxford. My background is particularly looking at problems to do with mathematical finance and optimal decision making. I've got a big interest in understanding risk and uncertainty, how that plays out in financial systems and how that influences decision making in various contexts.
Thanks. And Michael, you're on mute.
Good afternoon, everyone. I'm Michael Robustness. I'm also a computer scientist, like Marta. My area is multi-agent systems, so I've been working for around 20 years on the kinds of algorithms and architectures that support collaboration and competition between different individual AI agents. More recently, I've started getting involved into in ethical AI because we started looking a lot at systems where the agents are actually people, like online web platforms and social media and so on. And so my interest in operationalizing AI principles is around how we can translate some of these requirements to actual metrics, algorithms, and validation processes to ensure the ethical requirements are met.
Thanks a lot. So as everyone can see from the panelists, this session will be slightly more on the technical side, and so the goal here is to understand where we are in terms of ensuring in practice trustworthy. Is this technology ready to be technologies to verify and check that those algorithms do what they say on the tin? So I want to start kind of as a warm-up question. So, you know, many conversations that we have about AI and various opportunities and risks that come with this are quite high level. So at least for me, someone who's coming from maths department, sometimes it's difficult to pinpoint actually, you know, what is the core of the issue. So I thought that maybe, given all of you have slightly different background, if each of you could tell me, I'll give an example of an application introduces new risks and what those risks are.
Shall I go first?
Maybe if we go in the same order. Yeah, sure.
Oh, Marta, please.
Okay, do you want me to go first? Yeah, okay.
Yeah, please go ahead.
Yes. So, of course, from my point of view, predictably, I would say that that the main type of risk that I would be worried about is software failure. And these can manifest themselves in all kinds of ways. I will not kind of discuss in detail or draw any conclusions, but we've already had fatal accidents of autonomous cars. So these are the really high stake failures, but they can also come in a much more benign way. You could have a decision which is made by an algorithm, and it could be a decision about a loan, it could be a decision about parole, and these, if they are incorrect, for example, unfair, and in fact these failures have already happened, and if we do not understand why these decisions have been made, then this is a significant risk, especially as AI technologies are being deployed across the whole range of domains.
So you're touching here upon the challenge that effectively we're dealing with a very complex black box models, and as we're deploying them without necessarily understanding of the inner working, that might manifest itself in a number of risks. Okay, thank you. Sam?
So, well, there's a few things. In finance, there's been increasing concern about such things as flash crashes, where we see algorithms that are interplaying with each other and causing trouble in financial markets. So that's a simple thing. But you also have the regular risks as AI gets used more and more. It leads to other concerns, so data breaches, privacy, all those sorts of things. And also, I suppose Marta mentioned autonomous driving, people putting overconfidence in AI systems when they work well usually, but they're not as reliable as you think they should be.
Yeah, thanks. I think that the important point that you've mentioned is that there are individual risks from the perspective of specific use cases, and there's the systemic risk as you gave example of the algorithmic trading in finance, where you can have interaction of algorithms, and that interaction adds another layer to the challenge that is already there from even a perspective of a single algorithm. Michael, anything else you'd like to add, or any other applications you'd like to mention?
Well, I think apart from kind of applications that are high risk or in very high risk domains, I think the other big thing we're seeing is that the AI algorithms that drive the world's search engines and recommendation systems and online marketplaces and so on, there are very subtle ways in which the results of these prediction and personalization mechanisms actually redistribute attention, information, even resources and wealth and money directly in a kind of very in a way that's hard to observe in terms of the impact of each individual by every decision, but it has a massive scale if you look at it globally, and it's kind of quite subtle and it goes on behind the scenes. And I think the main risk comes from the lack of kind of governance, that we don't understand very well what the standards are that all these big providers are setting for themselves in terms of fairness, in terms of how we allocate benefit and sometimes punishment in just ways, in fair ways, and that then things happen without us being able to anticipate the risk and actually mitigate against it. Okay,
thank you. Yeah, so that actually moves us smoothly to my second question that you've already touched upon towards the end of your answer. So this concern, has been there for the last couple of years, and as a result, all the major regulators and big organizations released the principles for safe and ethical deployment of AI, trustworthy AI, and now I believe that as I've seen someone counted. So we have those high-level principles, and I think I haven't read all 150 of them. I read maybe 10 or 15 of them, and they kind of all look fairly similar. So on that very high level, I think there is a consensus. There is agreement that we all agree what AI should be and what it shouldn't be, and how they should be used and how not. But the challenge, of course, is how we go from those high-level principles to actionable frameworks. So of course, this is a very complex problem, and I'd like to hear some of you. I know you have different pockets of expertise. There is fairness, there are various challenges about metrics, and can we quantify fairness really? Is that feasible? I think that could be a discussion for the whole panel, I suppose, but we need to be brief here. There's explainability, the privacy and utility trade-offs. So if you could maybe comment on some of those challenges of translating principles into actions. I don't know, maybe change the order, Michael, if you would like to start.
Yeah, so for me, the main challenge is that everybody agrees on the principles, even though there are some subtleties around how you would interpret them based on your cultural background or the kind of the community you're talking to and so on. The main issue is that they don't really say very much about how you reach consensus on how we translate them to quantifiable things. So because we're using computers and numbers, there is no way around having quantifiable kind of and verifiable kind of standards and metrics. So if you look at, for example, fairness, people are normally talking around kind of 20 different metrics. But what's harder to pin down is, well, what is the acceptable threshold for discrimination in a particular domain, in a particular area? And how will the different stakeholders involved in setting these standards, how will they reach consensus? So if you look at other industries, safety critical industries, there's a whole kind of pretty heavy institutional scaffolding of standardization bodies, industry bodies, and governmental organizations. And in a sense, what these principles don't tell us is how do we translate it, to get to the point where you have the standard or the figures against these requirements that then those who provide the products and services need to adhere to. I think that to me is the main challenge, that most of these principles are very little about process and actual how you get to a quantification.
I think Lucas just frozen. Maybe Marta, do you want to?
Yeah. Okay. Okay. Yeah. So yeah. I will pick up. I think at the point where Michael's. I completely agree. With Michael that in safety engineering we have standards, we have processes, but what we also have when we talk about aircraft safety engineering, we have a lot of mathematical theories. We have, dynamical systems, we have methods, we have techniques and tools where you can actually set, this is the standard, for controls they want to achieve. And then you find an appropriate, the theoretical design of the controller, which you can adapt to your situations. So, you can, you are working with theories that can actually give you predictions. Now, in contrast, when we are looking at machine learning, most of AI is data-driven. It's based on machine learning. That means that someone has chosen a set of training data, usually with some labels, even supervised learning, and then it's trained a model. Now, training that model involves running optimization with some randomness. So you can run the same model with exactly the same parameters, and you would get different accuracy and slightly different results. On top of that, the decisions that the model has made are just completely unclear, because what we have is we have an artifact that has been achieved through some sort of running and numerical optimization software, and we do not see it in terms of decision trees unless it's a very simple model. So these artifacts are black box and are very difficult to interpret. And as part of that, it's even if we have some input from the application domain about the appropriate level of discrimination, we at this point in time cannot align that with the actual theoretical underpinning of machine learning, because it doesn't exist.
Yeah, thank you. I mean, that's interesting. I'm particularly the point when you mentioned that there is a whole body of applications in engineering where there is some physical reality, physical laws that are holding things together, and there is a combination of that and model, and you can isolate certain sources of uncertainty and try to understand them. Whereas here, especially in some applications to, in a social context, or for example, economics or finance, this is much, much more challenging. Some uncertainty is one of the topics that you like a lot.
Yeah.
So perhaps you have some thoughts on that?
Well, so the difficulty is not just in explaining what these systems are doing, as Martha mentioned, but it's about even knowing how accurate they are. And because we don't understand the black box, we don't have a good feeling for how reliable it is. And we're often trying to deploy these things in systems where they are big and complicated, and we don't know enough about how they'll perform. In some ways, that's what we're used to in most engineering problems. We've been applying whatever we've done in systems we don't fully understand. But now we're able to do things at a level of subtlety that we haven't been able to do in the past, and also in a way that the speed of what we can do and the scale of what we can do means that we need to be a lot more worried about automating that management and observation type system. I suppose one other thing, drawing on what Michael mentioned earlier, there's a lot of trade-offs in applying machine learning AI systems. The fact that we can do so much more with data means that using data becomes a lot more valuable. But then we also know that other people can do a lot more with data as well. And so we need to really increase our worry about privacy. So you can see the fact that whenever I go on a web page, I now have to click what I'm agreeing to exactly is a fairly obvious manifestation of this tension between privacy and utility, but it exists in many other areas as well. The fact that health data, there's so much more data that's being collected that you could use, but this data is very sensitive. It's talking about people and the tension of how do we decide what we are going to allow to be done with our data, possibly at arm's length, where we're not working directly on it ourselves, we're allowing other people to work with our data, and how do we decide who makes those decisions is a difficult set of challenges.
Yeah, thanks. I mean, one other thing that just came to my mind as you were saying is that, maybe historically and again, coming back to what Marta said, when in engineering applications or even in finance, in some very complex investment banking departments, the people that were doing that job and that were using the sophisticated models and technologies were very well trained. Whereas the part of the, maybe, I don't know what's the author's challenge now, is that it's relatively easy to use these very complicated models because of the open source software, and therefore people that maybe don't have a huge experience on working with data and complex modeling all of a sudden can start producing something that looks good. Is that additional
I would add that another danger is it's not just, I think it seems that it's easy to use these models, it also seems it's easy to develop these models. Because, you know, there are only a few lines of TensorFlow. There is a lot of open source software. You've seen something trained on another data set, you apply it to your data set, okay, and then that's the start. But of course, debugging these models is very difficult, because debugging means debugging the data. So if your data is poor quality, you just don't know where to start. It's not like debugging a piece of code, which is a few lines. It's debugging the data.
That's a very good point. Yeah, thanks. Okay, I want to move to the next question. Maybe Michael, if you could. So a big chunk of research or academic research that falls under the umbrella of Trustworthy AI often takes a single agent perspective, is looking at the algorithms or certain challenges from only one angle, whereas lots of those issues, I mean, some touched upon that, I would argue falls under the umbrella of multi-agent systems, or we need to think about this in a more systemic way. I know that's a type of research and work you've been doing. If you could share your views with us on that and tell us maybe a little bit about your research in that area.
Yes, of course. I mean, I think the real the perspective I take that is multi-agent on this is that how you understand when you have conflicting different interests, what an agreeable solution is on what the overall, you know, ethical or appropriate algorithm should do. So to give you an example from work we've done is, you know, you can have if you have some sort of limited resource that you have to distribute over different agents. So let's say the different providers on a hotel recommendation website are vying for, you know, which place their offer should have in the ranking. And of course, there's only so much attention that the viewers of that website will have. And then the idea is, of course, somehow this ranking algorithm should sort them in some sort of way. Now, you can, of course, ask them all for their pricing and for the properties of their products and so on. And then the question is, how do you, what would the algorithms look like that produce a fair ranking? And one type of research we've done is that, you know, we go to people, to normal users of systems, and we say, well, you know, should we allocate these positions randomly, or should we, for example, prioritize those services and products that are more popular? Should we make sure that everyone gets a chance every now and then to get some exposure? So it's really about it's a little bit like asking citizens what the tax system should look like. You know, that's fair. You know, how do you distribute the tax burden among people based on different properties, based on their income, based on their, you know, you don't want certain things to creep in. You don't want to tax different people differently because of their different ethnicity or gender, of course. So so the reason I think the multi-agent perspective is important is that there are very few systems where only one stakeholder is involved with certain preferences and needs and desires and objectives. So we have to think about how we balance those. And this is, I mean, it may sound rather abstract and complicated, but it is actually a very practical issue. So if you think about finance, how would you decide what type of people should get what allocation in all the available credit? Right, so the lenders have an obligation to provide access to finance, of course, only if it's affordable to the person taking the loan or the business taking the loan, but they have some obligation to use their assets to support kind of, you know, people's business objectives and private objectives, and to help them grow financially. So, but then if you ask them, how would you split that pie? You know, should you provide weaker people with more finance so they can improve? but then maybe that creates too much risk because they might not be able to repay this debt. Should you focus on the underprivileged because there have been systemic problems in the past, and maybe black people got less credit than white people? Should you therefore discriminate positively? So there's all these questions which ultimately all boil down to the same issue, which is, well, if you have conflict of interest, how do you what should the criteria be by which you make that judgment when resources are limited? And so I think even when you look at a self-driving car, for example, which sounds more like a single agent problem, you actually have to consider, well, how does it relate to the driver? How does it relate to the people, the pedestrians it might run over, or other drivers? So it very quickly becomes a multi-agent problem, which I think, and I think we're still far from being able to look at that dimension in the really complex new AI systems. It's very tricky.
I agree, tricky and very, very challenging. But it's actually closely related to the question I had for Sam, that this trustworthy AI and research on that, to a large extent, is being developed in computer science departments. Of course, there is, for the last couple of years, we've seen many ethicists that engage in that conversation and providing that thoughts, and that's really wonderful. However, maybe I wasn't looking properly, but I haven't actually managed to find too much work trying to connect those issues with some research or mainstream research in economics, and lots of ideas that have been developed over the last, 70 years that I think fit quite well. And I know, Sam, you've been interested in that intersection of research in risk and economics. How you feel about this?
Well, yeah, there's obviously quite a lot of interaction, as Michael was saying. When you've got a multiple agent system, you've got to understand how different agents are acting. And I suppose you've got all the theory of things like principal agent problems, which is about how do you design incentives to make other agents want to act the way that is in your interest or in a socially good way. You've got questions of moral hazard. So this is connected to what Marta mentioned earlier about self-driving cars. And that's really, that's where by making a system seem safe, people act less safely in that system. And so the people who've had accidents in self-driving cars, in some cases at least, it seems they were watching Netflix on their phone while driving, which they wouldn't do if they didn't have a self-driving car. And so you need to take this bigger perspective, not just on, is the system safe in itself, but how is it going to be used? How is it going to be implemented? How are people going to be engaging with this system? And there's thinking in economics, but there's also thinking in other areas of engineering, which I think is coming into the considerations around AI. Maybe Michael or Marta may know more than me about what's been happening in that direction.
I mean, I would just very briefly comment that I think you're touching upon the right point there. I think traditionally, of course, economists don't look at things from an engineering perspective. And maybe there's a gap there that we need to fill.
It sounds like that. It sounds that we just maybe scratching the surface with the with all this research on trustworthy AI. So going a little bit more towards a practical tools and technologies. So Marta is a world-leading expert on validation and verification of theory and complex decision-making systems. Could you tell us a little bit about your work and what hides behind the term validation, verification, robustness? These are sometimes used exchangeably, and maybe the meaning in the context of black box complex algorithms is slightly different than what it used to be when applied to simpler, tree-based methods.
Yeah. Yes. So for those of you who are from software engineering will have seen V and V, that stands for verification and validation. Now, validation just basically answers the question, is my system fit for purpose? So you typically have some set of inputs, and you test the system, give the inputs to the system, and you check whether this is the correct response. Now, verification is about providing a proof, which could be done, by mathematics, by a theorem prover, but also by a piece of software, that the system's response is correct. Okay, it's correct with respect to a given requirement. Now, these are actually different, because you can have a system which is correct, that is, correctly answers all the questions that you give it, but you've forgotten some very important requirements, so it's not fit for purpose. And this is quite a common occurrence. Now, for machine learning, we tend to talk about accuracy, and this is typically measured by the percentage of answers that the model gives you that are correct on a test or a validation data set. But what we also worry about is robustness, and that is, if I take an input, but I know that my input are subject to some noise. So if I manipulate the input in some very minor way, can I guarantee that the system's response is going to be also sort of, varied in a very small way? Now, if the system's response is kind of catastrophically different, this is instability that's similar to what's happening, in control, and these are the situations that we want to prevent. Now, these manipulations, of course, they could be because the input distribution has changed on the data, or it could be because there is an adversarial attack. So we can talk about adversarial robustness in that case, and what we want is we want to have provable guarantees that my machine learning model, which I've trained, actually, gives me answers, perhaps with some probability, or perhaps, with high probability, or even, I can guarantee that the probability is going to be at least, say 80%. So that's what verification is about. But I also want to link to what Michael and Sam was saying, because a lot of my work in verification is actually for multi-agent systems, except that we call them games. I work with stochastic games, concurrent and turn-based stochastic games. These are the same things, and economists have studied them. They are, I think, very good for representing complex decisions, not just complex decisions, but also incentives, rewards, etc. And for that, what I'm working on is essentially developing tools where your questions for verifications are of the kind, if I want to apply for a particular bank loan, is there a strategy for me, within this complex system to actually get the bank loan? That's a game theoretic question, because you can represent it as a winning question. But also, I can ask my system, can you give me that strategy? So that then I understand the steps that I have to go. But for a bank, the kind of things that I wanted to move towards is how can the bank design the system so that people cannot game this in ways that the bank does not want users, clients to game the system.
I suppose if I can add something to that, one of the challenges we face, though, is when Marta was describing the idea of changing the distribution just a little bit, that becomes a very delicate notion and depends a lot on where you're applying the problem. And this is one of the things with the, I suppose, democratization of machine learning and lots of people applying it to a lot of different problems. Those different problems are going to need actually different solutions, different ways of perturbing the inputs. They're not necessarily the same, because when you've got a lot of data and you're in very high dimension, these things can look very, very different. And there are good mathematical reasons why that's the case. And so we need to not be too naive and present a panacea to these problems, which we say will work in every situation. You need to do things that are relatively bespoke. And that means you're still going to have people who need to understand the systems, understand what's going on, and who can then think of how to appropriately build robustness and management in that situation.
Yeah, I agree. And I particularly, I think this aspect of gaming the system is very interesting and challenging in deploying AI in the wider economy. So with that, yeah, Michael.
Yeah, no, I just wanted to say maybe also for the benefit of the audience, some of the things we're talking about here are really pretty advanced and pretty you know, a lot of this is kind of ongoing research and you know, requires a lot of deep understanding of very, very specialized mathematical and computational tools. And yeah, I think we've seen in the past, and Marta has much more experience than me in that respect, but how you know, very specific industries started adopting some of those things and developing the skills that are needed when it was necessary because of the safety risks that happened. I think what we're seeing in machine learning is, of course, you know, armies of people trying out all sorts of things around the world in systems that might even mutually interact with each other, largely not made by people who use all these very advanced techniques to verify and validate and test things like, you know, gaming of specifications and you know, the systemic dynamics. And very often an individual business may not care directly about the systemic dynamics, you know, will not see it as their responsibility. So I think there's also something about where that the adoption and application is advancing in some sense faster than the skills to you know, do the due diligence, which I think is a challenge.
Yeah, I agree. Thanks. So with that, you know, I'm thinking, you know, kind of a picture that emerges a little bit from this conversation. What was my intention to stay a little bit on the technical side is that these are all very, very challenging problems and active research area. So I wanted maybe slightly provocative question, I don't know, depending on the perspective, is do you think that this technology, AI, machine learning, is ready, or how close maybe it is to be ready to be deployed for the high-stake decision making? So what I'm trying to say is that, you know, we got all very excited by some early successes of AI on, you know, image classification, which is very challenging computer science problem, but very, very simple. If you think about it, it's just lots of pixels. The dimension, the apparent dimension is high, but the data sets are static, and you know, at the end of the day, it is relatively simple in comparison to, for example, designing a financial system and with using or automating things in the financial system. The other applications that we've seen that also make people or give people believe that this technology is extremely advanced is coming from, say, DeepMind, where people see, you know, playing Go or playing StarCraft, that this technology can do extremely well. But then again, these are the situations and applications where we can relatively simply simulate the environment and we control pretty much what's happening in it. That's very, very different to real life with all its complexity. So is this technology ready to be deployed? Do we have it all in place, or we need to be very, very careful?
We only ever deploy technology that's not quite ready, because we only ever figure out what the problem is once it's in play.
Yeah, well, this technology is being deployed, as you know, how many of you own a Tesla? So Tesla, you know, has an autopilot, and it's working. It is actually working. It is, you know, employing actually image classification. It's running, you know, a huge planning problem. But the Tesla solution is that whoever buys the car, they are responsible. Tesla is not responsible for any failures. So it's a very good way to actually test the software. We know Uber, you know, is also testing the software. But at the same time, you know, so we are just pushing and pushing the boundaries and learning. But for now, there is no theoretical basis in the sense that, you know, we have a theoretical basis for how to fly an aircraft, you know, have a dynamical system model. We do not have that yet for these situations. And, you know, even if we did, if we deal with environments that can suddenly change very fast, then what we also need is we need a capability to monitor the system and perhaps stop it by something like a fail-safe action, you know, to have some kind of control, monitor and control loop.
And what about uncertainty? So you've mentioned that those models have quite a lot of randomness in them, can be unstable. Do we have methods to quantify that uncertainty, particularly in the dynamical settings?
Yes, so there are already, you know, for machine learning models, there are neural networks with, you know, a Bayesian variant of neural networks, which has a prior on the weights. The issue with those is that if you want to apply them to a problem which is high dimensional, then the ways to compute the posterior probability to compute these uncertainty, that's not the same as calibration. To compute, these are intractable. So we only have approximate methods to do this. And to improve on that, we need better maths, we need clever maths, clever numerical methods, and better computational techniques. But this is just to compute, for example, the posterior probability. This also needs to be calibrated with respect to experimental evidence, you know, the actual failure probability.
Okay.
And I think what we're not so clear on, so there's a lot of work going on in this direction. How do we compute uncertainty? We're also not completely sure, even if we could compute it, what would we do with this computation? We don't have really good ways of understanding how this would change our actions, how this should change our regulations. Those are things where there's lots of different ways that you could try and apply an uncertainty-aware framework to various problems, and which ones would work and which ones wouldn't work will depend on the application, and we haven't got the experience yet to know what's a good way of doing this and what isn't. The tragedy is the only way we're going to get that experience is by watching it and hopefully catching things before they go horribly wrong.
Well, I mean, I think to some extent for me, this is always about, you know, programming, testing, and modeling and developing a mathematical model and so on. In some sense, these are always ways in which you communicate and you interact with a system that's hard to understand. So if you think about medicine, of course, we don't really understand how the human body works, but we have in detail on a case-by-case basis for every patient. We have statistical models, we have partial kind of theories that we know causal relationships between what happens in the body. But quite often these are abstractions and we can't put them all together. I mean, that's just too much complexity. So what do? Sometimes we do a bit of trial and error. We do it in a measured way. We do it in a, you know, if you think about drug testing, we follow very specific protocols to learn more and increase our confidence. but we also engage in the human and the social process of agreeing what acceptable risks are and weighing different risks against different benefits. And I think at the end of the day, for any sufficiently complex technology, probably that's the best you can do, because in a sense, you can't, I mean, we're talking potentially about phenomena here like the global traffic system, the global financial system, the global healthcare, you know, so these are all things where, and I think there's almost kind of a philosophical limitation, which is, if we fully understood how it works, we actually wouldn't need AI. We would just like hard code and program something that solves the problem we need to solve, right? I could just write the code for the self-driving car with human intelligence. The reason we're using these data-driven methods is because we're trying to find approximations from observed phenomena. So in some sense, we're introducing some intransparency that we're benefiting from, and then we have to recover some of it to make sure it works, and we're happy with the guarantees we can provide.
I agree. That aspect of ability to measure risk and measuring those uncertainties is the key in helping making those decisions. So, talking of things that some you've mentioned that can go horribly wrong. So, you know, my background and yours as well is coming a little bit from quantitative finance. So when I'm thinking, I mean, there is to some extent some parallel between AI and finance in that in at least some parts of financial systems, people have been using very complex models. You know, arguably, you know, we can have a discussion what's more complicated, whether some horribly complicated econometrics model versus neural network. An industry is highly regulated. There are regulators, there are principles, there are recommendations, there are big departments within finance organizations. I like finance as an example because unlike some other industries where we're trying to use AI, this is an industry where there is history of working with data, there is a governance structure, and so they're kind of a little bit step ahead. Nonetheless, despite all those regulations, despite all this care, every now and then, you know, we witness financial crashes happening. You know, 2008 comes to mind. Can we draw some parallel? If you maybe could tell the audience about, you know, give a little bit of a background about financial crash of 2008 and how this could be connected to some of the things that we're trying to achieve with regulating AI.
Well, how long have you got?
Well, we have about 10 minutes.
I think the 2007-8 financial crisis is actually a really interesting object lesson in this space, because it's got a whole lot of things that went wrong. You've got a problem in regulation that finance, there are multiple regulators all doing little different pieces. And one of the issues in the 2007-8 crisis was that the regulators almost had a bit of a turf war over who was meant to be regulating what. So I noticed in the chat there was a question, should there be a unique standard setter or should there be sector specific standard setters? I think practically there have to be sector specific standard setters because you don't have the expertise to do things, because different areas require subtly different regulations, subtly different standards. So you have to do it separately. But if you're going to do it separately, you then end up with the politics of multiple overlapping regulations. You then had very complicated models, but in some ways too simple models. The models we used in finance, they were too simple to capture all of the risks that we had, but they were too complicated for us to understand. And I think the same can be said about a lot of AI systems. We know they're not complicated enough, they've not got enough data to capture everything, but they're also too complicated for us to understand. And what happened was that people then started to rely on these models and to believe that they'd captured the risk and they'd captured the uncertainty. And so you ended up with this problem evolving with different institutions offloading their risk assessment to regulators or to risk ratings agencies, those agencies not having fully developed risk capability and so not giving back reliable answers. And so you end up with this sort of all sorts of different problems all happening at once. And it's sort of the sad thing when you can see that in some areas of the application of AI, similar things are happening. We've got the same sort of complicated models, but they're not good enough to capture everything. We've got the suggestion of we should be regulating, but it's not clear that regulating and ratings is going to actually resolve the risk. And it's not clear that passing the buck on to a regulator is actually going to solve the problems we have. And I think it shows us that ultimately there still needs to be the clear fail-safes. There still needs to be a good dose of common sense in the application of these problems. Because when you look at the problems behind the 2007-8 crash, it's common sense. It's not a good idea to be giving a lot of loans to people with no income, no job, and no assets. These are not safe loans to be giving, no matter what you do with them afterwards. But that's what the system was built on, and various magic occurred to make these things look safe. But if you think about it, it wasn't. And I think that dose of common sense was missing there and maybe missing in many of the applications of AI now, which is a worry. But just like in finance, when people are making money, it's hard to be the one who comes in and says, let's not do this. When the AI system is performing well, it's hard to be the one who come in and say, let's all hold back and not exploit these big gains that are available to us because we think there's a risk that something might go wrong.
Yeah, I think, that's, thanks for bringing that up. I think that providing this false sense of security by various models that are being now used and to help us provide some trust around AI, we need to be very, very careful about this, not to repeat 2007-8 financial crisis in AI. I'm being told by Adriana that our time is up. So thank you very much for joining the discussion. I really enjoyed it. I've learned a lot from you. Hopefully the audience did too. Thanks to Adriana and Emre for putting together this very interesting conference. And yeah, thank you, everyone.
Thanks.
Bye.
Thank you.
Bye.
Thank you.